Well, hi everyone. Welcome to session 6. And today's topic is computational thinking. It corresponds to the chapter in the book, chapter 7 of the same title. Before we get into it, I just want to talk a little bit about my experience as a student. And I'm doing this because as we get into chapters 7, 8, and 9 in the book, there starts to be a lot of overlap. Experiential learning, embodied learning, computational thinking, often they sound like they don't go together, but they can all fit into this area perceived as the maker movement. They have a lot of similar roots in terms of some of the work with a fellow named Seymour Papert, who we'll talk about today. And I should apologize for people who've taken my STEAM course last year, EDUC 117. There might be some overlap in the next couple of lectures. So just keep that in mind as we go forward. When I was a student in university and considering becoming a teacher candidate or going into education, I talked to a friend of mine who was an artist, and I think I was probably 23 at the time, and he was probably all of 27 or 8. His name was Wayne Giles, and he was an art student, and I think he'd been in law school as well. And I told him I was going in to study education, and he said something really interesting. He said, I wonder if they still do in schools what they did when I was in school, and which was probably like not that long ago. But I asked him what it was, and he said, "Well, if you were really good at something, if you were skilled at it, you just did all sorts of things in that area, and if you weren't good at anything, you really didn't do very much in that area. So if you were good at phys ed in high school, you spent a lot of time doing phys ed, and if you weren't good at math, well, you didn't have to do too much math, and if you were good at math." You spend a lot of time doing math and calculus and physics courses and not much time in phys ed. And he said, wouldn't it be interesting if we flipped those things around? So if you were good at something, you wouldn't be able to do it in high school. And if you were not good at something, you'd spend a lot of time doing that in school and in high school. At the time, it seemed like a great idea. It still does seem like a great idea. I don't know if students would feel too comfortable about it, but it makes me think about some of the things we do in education, particularly when we get into areas of STEM and STEAM and computers and the great outdoors. And about 20 years ago, when robotics were first coming on the scene, I was invited to participate in a gifted education course for young students at the university. And it was a robotics course. And I went over to the lab, it was in a computer lab, and I walked in. And the first thing I noticed was it was all boys. They were all 10, 11, 12-year-old boys, and there were no girls in the class. There were probably about 15 of them. They were making robots using Mindstorm's NXT, the early robots from Lego Logo. I also noticed that these boys didn't look all that healthy. They just didn't seem like they'd been outside very much. They were pale and thin, and they spent a lot of time in front of computers. And even though I was an educational technology person, I worked with robots and I worked in the software industry. I thought the part of me that was a teacher said, I'd just give these kids a ball and a stick and tell them to get outside and don't come in until they played themselves out or had too much sun or need some water. But it made me think about this whole distinction between spending so much time with computers and not being outdoors, and how there should be some kind of balance in school classrooms. And I hope as teachers, we can all think about this and make sure our students are leading balanced lives in the school. And hopefully they'll lead balanced lives outside of the school. And I think in a location like the Okanagan or wherever we live, if it's a nice day outside, children should be outside. That's my philosophy on it, and I'm not sure if everyone agrees with that, and I think really every school should have covered outdoor classrooms so we can go outside and learn out in the fresh air and the sunshine. Just an idea on my part. And I don't think it just ends at K to 12. I think it should happen at universities too. I've talked about this a little bit, that every university should have maybe 7 or 8 outdoor classrooms that have facilities to show slides, to use computers, but are definitely outdoors. So with that preface, the textbook today, the chapter 7, talks about math and STEM as these areas that computational thinking supporting problem solving. They talk about, and one thing that comes through a lot in the chapter is the need for professional development for teachers in this area. Very strong area of need. It's a short chapter again, but they do 8 eight things that can add to the efficiency or effectiveness of implementing computational thinking in the classroom. One of them is to promote a model of use, modify, and create. So instead of students just using computers and downloading things and using, they can use them and modifying them, and then creating new things on the computer. The name for that actually, that doesn't mention in the book, but a good name for that is hacking. And I'm going to show you a hacking site today that we can go to, and you could have your students go in and alter things and just see how they look. They also talk about 6 challenges. And again, one of the really strong concerns, main concerns, is this lack of resources, lack of information, and lack of professional development for teachers. There's computers, robots, all these things are in the curriculum, coding, but are teachers getting enough training and professional preparation to teach these areas effectively? And once again, I go back to my point. It shouldn't just be about computers. Every hour a kid spends on a computer, they should probably spend an hour outside. So, with that in mind, I'm going to go and look at some sites I put on Canvas today. Uh, One thing that I've done in my career is I've participated in creative coding. I've worked as a computer artist, and I'm just going to talk to you about genres of creative coding. So, coding is done for creative expression rather than function. So it's not to make databases or calculate figures in spreadsheets. It's done to create music and art and drama and dance and materials and fabric and all sorts of things that people are using computers for that don't necessarily uh, align with the functional use of computers. I'm also going to show you Scratch, and I think if anyone is trying to get into computers as a teacher and you're teaching between the grades of 2 and 8, you should learn Scratch. It's a fun area to get into. There's lots you can do. If I was teaching at this time, I would be using Scratch in just about every subject. I'd use it for art and language arts and music and science and math. And I'd have students make Scratch animations. It's a great platform to make games on as well. So we'll go in and look at some of these sites. I've decided to forego robots today. We'll do that next week when we get into maker movement, because robots do fit in there quite nicely. And I'll spend a little more time on that next week. So today we'll go into Canvas right now, and I'll go through the sites, and we'll take a look at how computational thinking and computer programming can be constructed in school classrooms. The first item on Canvas is a cartoon image, and it's just 10 reasons to teach coding. It's from BC Education, and I'll just go through them briefly. Coding allows students to create content, not just consume it. So it's that use, modify, and create model again. It empowers students to give them tools to express themselves in cool ways. Number 3, it teaches storytelling with games and animations, especially with a program like Scratch. Number 4, it's a place for students to take risks and fail safely. 5, coding is inclusive and builds self-confidence, which it can do. 6, coding supports many principles of mathematics. Computer programming is generally thought of as being about math, very math-oriented and STEM-oriented. 7, coding teaches problem-solving, critical, analytical thinking skills. 8, it's a new type of literacy and will be a large part of future jobs. 9, coding develops teamwork and collaborative skills. And 10, it can help humanity. A very general, positive view of coding there. Those again are from BC Education, and they do kind of provide a rationale for why to teach coding in schools. Second thing I put down is just a another site from BC Education. It's a link, and it brings up some activities for introducing computational thinking in the classroom. It's focused on elementary grades, and there's ideas about programming, having people move around the room as if you're coding them, as if you're programmed to turn right and center, left and center, and go backwards and forward. So it's a unit introduction to computational thinking. You may find it useful if you're teaching computational thinking in an elementary classroom. There's about 4 activities, and ping pong rescue is the first one. One involves pizza making, and they just teach ideas, basic ideas about coding without actually being on a computer, because computational thinking is not coding, according to some experts with BC Education, and coding shouldn't start till, say, middle or even grade 9. But a lot of things children are doing with classroom practice and visual language programs like Scratch, they're doing coding. There's no doubt about it. I added an article about Seymour Papert and Mindstorms, which is the name of the book he wrote in 1980. And if you don't know much about Seymour Papert, you might want to read this. He developed a computer language program called Logo, which was designed for young children. It was based on another language called Lisp. And through that language and his book, he came up with this idea of guided discovery learning and also this notion of constructionism, that students will learn much better if they can work with models. It's almost the idea of embodied learning, which we discuss in chapter 9. But he was a student of Piaget's, and he incorporated Piaget's ideas and said they could be promoted if students could work with models. And the model he built was this programming language called Logo. There's a shot of him at the end. Here's an image of the turtle moving around, making geometric shapes, coding in the language. And this is Logo language down here. It's telling the turtle to go forward 100, right 90 degrees, and then forward another 100 degrees. Um, at the end, he's developed an original turtle, and which was a robot called the Turtle, and there's one right there. They proved to be too expensive for schools in the 1980s, so they developed virtual turtles, and they became little turtle images or rectangles on the screen, which we see in this case. That little thing right there is a virtual turtle, just a triangle on the screen. Sorry. So you might want to read that if you haven't had anything to do with Seymour Papert or Logo. It gives a good background, and truly, he is a real key figure in what turned into the maker movement. This idea that we work with models, we make things, we construct things, and teachers serve as guides on the side while students uh, go around problem solving and using induction and reasoning to solve problems and work on projects. I added another link on, well, this is actually a slide set that I came up with about creative coding, and that's what I do. And I'm just going to go through it as quickly as possible. I don't want to spend too much time on this, but it's the development of creating coding and coding genres. And what is creative coding? Well, it's a broad field of technology arts in which coding is done for expression rather than function. It's not working with spreadsheets or databases with figures. It's working with stories and ideas. I started out doing computer graphics many years ago. These images are probably about 35 years old now. And I just started drawing on a computer, looking at things I was interested in drawing, which were reflections and light. But as I used a graphics package and a stylus, I didn't really know what I was doing. I mean, I could make images on the computer, but I didn't know how the computer was processing those images using algorithms or functions that would generate images on screen. And I went to a few computer graphics conferences. I learned a little bit more, and then I started coding a bit more. But there are advantages to coding. Uh, like I said, many artists don't understand. They can use digital tools, but don't necessarily understand how they work. Uh, Artists can explore digital structures, bit mapping, basic mathematical algorithms used to generate imagery and sound. They can start hacking. They can express their ideas through coding. They can be closer to the inception of the design, and the artist can have more control over these processes if they understand how coding works. Coding for expression would place arts in the heart of STEM, and it aligns with many new curriculum initiatives, creative competencies, coding literacy, also transferring ideas across disciplines. It's transfer of ideas as well. And explores thin aesthetics, which brings the senses together. Listening to colors, virtual music, sounds. A lot of computer art activities and projects involve really odd things like listening to colors and drawing with sounds and dancing to colors and things like this, which is generally referred to as synesthetics. It's this transfer between senses. Um, there's genres of creative coding, and what I'm interested in is generative art. So you generate new output every time the art code is run. You put in random elements in a program, and it creates pieces which are completely different. This is sort of an emulation of it, but these diamonds might turn into circles and then turn into pentagons and then change color and fill up the screen. So this is just an example of what generative art might look like. Another genre is interactive media. If you've ever been to a simulation place or a virtual studio, you can work with a program called Tilt Brush, and you can create images virtual images, and then you can step through them and color them and paint them and go inside them. This is a Google product called Tilt Brush. It's been around a few years. Another project that was developed many years ago is called the Very Nervous System. It was developed by a Canadian named David Rokeby, and he used video cameras and computers and a sound synthesizer to generate music that you dance to, and the more you danced, the more music you made. Really interesting concept. Data visualization is a third genre. These are actually books in the Bible and cross references between them, but it's a way of representing data that's not normally represented this way. This is kind of a graph, but it's very different. It's a visual design and it's an art project. Um, these are some more visual representations of data that kind of form a new way of mapping. Projection mapping is when you take a surface area for a computer and you can project it either virtually or physically onto an object. It might just be a sphere or a cube, or in this case, it might be the Sydney Opera House. Augmented reality, this isn't art, it's actually a project from Costco, I think, to show you how you can decorate your new room. But you can use augmented realities and virtual realities and create art this way. Uh, Pokemon Go is another a version of that, and you can take it outside and you can add computer-generated elements to real-life situations. Sixth one is spatial sound, manipulation of sound or music in a 3D environment, and allows an audience to be completely immersed in an audio landscape. Seventh one is art games. They're computer games, but they really are designed to show off artistry and artwork. This one's called Samarast, and this one is called The Endless Forest. The eighth one is soft circuitry, and it's fairly big in the States, and it's actually using fabric or paper or other soft materials, and you can enhance fashion with elements of light, sound, video, or interaction. And these are just some ideas of what has been going on in schools. It's quite a big deal in American schools in some cases, and it allows what we regarded as home ec or materials courses to include computer technology and generating circuitry inside of fabrics and materials with lights and sounds. Creative coding in K to 12 or K to 8, I would use programs like, well, actually, I'd probably just use Scratch in this case. I put a whole bunch of them down. They're all very much like Scratch. They're visual programming languages. They were developed by Papert. Here he is again with his book Mindstorms. And you drag and drop blocks and build blocks, sort of like Lego, and you can set colors, you can set distances and directions in each block, and you can add variables. So this is called code.org. This is one called Blockly. They start to all look the same after a while. This is Tinker, another visual programming language using blocks. And this is Sphero. This is the one that uses to run a robot. We'll look at this next week. And then finally, this is Scratch. And it was the original one, and a lot of them all owe a great debt to Scratch. And they all owe a great debt to Seymour Papert and his logo language. I like Scratch. One of the reasons I really like it, you can make your own icons. You can add photographs. I presented at a conference in Winnipeg. This is the Human Rights Museum, and I just did a little animation of this bird, a dove or a pigeon flying around the Human Rights Museum in Winnipeg, which was fun to do. And I just did it on the spot when I was there. So you can add your own photographs, you can make your own sprites, images, you can add music, you can add sound, you can record your voice, you can put in your own movies. It's very, very multimedia format and really promotes creativity with children. And like I said, you can make your own games and tell stories. So Scratch is a wonderful program. This is a version of Scratch that's used to run a robot called MBots. And instead of the little cat that's used in Scratch, it actually has a panda bear. But it's very much the same program. And I'll show a little more of this one next week as well. Platforms for grade 8 and 12. Generally, they're called Integrated Development Environments, IDEs. And there's a number of them. Adobe Flash, Processing, Jitter, Open Framework. One I'm familiar with is Processing. People aren't using Flash very much anymore, but I have used Processing quite a bit. Another program is NetLogo. It was instead of having one turtle in Logo, think of having 50 turtles, and they can interact with each other. So that's basically how NetLogo works. A little more complicated. not very user-friendly, and there's not a lot of tutorials online for it either, but it's generally used to construct simulations at universities, but it originally was developed for use in schools. Um, and you can do artwork with Neck logo as well, and go in and hack programs that are already pre-existing. This is a site for openprocessing.org. It's a shared site if you're using processing, and you can go and look at other people's creative works that they've made. Processing, here's another art example in processing. Uh, that's it for the slide present. I put in some references and some references to the imagery in here as well. Another site that I added was just the Scratch, link to the Scratch website, which is right here. If you click on that, it will take you to the Scratch homepage. You can go right in and hit create and start creating right at the start, or you can log in. Now I've logged in, I have a username and a password, and I can go in and create. And it will come up with just blocks already to start moving. This is this cat called Scratch, and he's your sprite, the original sprite that you start working with. And you can drag and drop blocks over and say move 10 steps, turn, I'll just have him turn 45 or 45 degrees. And every time I click on those, he will move. And you can put in repeat functions. You can add a green flag. The really wonderful thing about Scratch that's just great, it has all these wonderful tutorials. And just go up, I'll just go back where I clicked that before. Just go to the upper bar on the left side right here, more or less to the left, and hit tutorials, and it'll just show you how to do just about anything, how to get started, animate a name, make a chase game, Pong games, record a sound, use arrow keys, make objects spin and add effects. And so, like I said, you can add games, do music, art, record sounds, bring in your own photographs, add movies. It's a really multi-purpose program for storytelling, for math, for games. You could have students do science projects, make their own tutorials for each other. So it's just a wonderful program. I won't spend a lot of time going through each tutorial with you, but there's lots of books on Scratch. I do find the software interface changes every 18 months or so. So if you buy a book, it might not look the same as the software online. And a lot of the books had tutorials, but now the tutorials are all online, right on the home site for Scratch. So the final link I have today is a Scratch link, but it relates back to what I said about creative coding, and it's Scratch generative art. So it's a number of people have made generative artworks in Scratch and have posted them to this online site. And I'll just go to that link. And what's nice about this site is you can go to it, and I'll just enlarge it, and you can take one of these art projects and look at it. This one is called Ghost Circles, and if we hit the green flag, that's how you start Scratch projects. There's a series of bursts of little circles, concentric circles that show up. The nice thing about this is you can go in and hack it. You can see inside the code. I'm just going to click over here on the right. And if I go in, it gives me a smaller image. I can change the size of the circles by, say, instead of 5, I'll just change it by 20. And we have larger circles now. And I changed it by 200. There's 20. They're about that large now. And other things I can do, I can set the color. I can change the color to pick random. I can also, these are stamping, but after each stamp is made, it's deleting the stamp, so deleting a clone. So what happens if I remove the stamp is the clones will stay, and they'll eventually build up into just a pattern of colors. They're not dissolving afterwards, they're staying there. So you can see it's actually, I'll just run it now and they'll build up that way again. I can actually change the size to, say, 50, and we'll run it this way, and they'll stay and build up. The concentric circles are quite large right now. So you can just go into any of these programs and start hacking, and it's a good way to learn how to code is to go in and just see what kind of code other people are doing and change it a little bit. You can see what happens, and you can just explore and experiment and take risks, and at the end of it, you can just stop it and restart it again with these programs. So it's actually a really good way to learn how to code. So today, that'll be it for today. Next week, We'll start on session 7. The chapter in the book is session 8, and it is on experiential learning. I'll look more at robots next week, and we're going to kind of delve into this idea of the maker movement. There's a great article I'll have for you next week. If you're going to read anything in the course, it's this one article, and it'll be posted for next week. And following that, there's just one final session on experiential learning. So that's it for today. Have a good week, and we'll see you in session 7.